Okay, in this video 3 of Module 9, we're going to talk about onto functions. In the previous video, we talked about one-to-one functions. Now we're going to talk about onto functions, which are also called many-to-one. So we have one-to-one functions, where each input has a unique output. Now we're going to be talking about many-to-one, or onto, functions. In this case, every element, a good way of putting this is that the codomain equals the range. Right? So, in other words, there are no elements in the codomain that are not matched to. So let's take a look at that. Okay, so a function is said to be onto or surjective or many-to-one if and only if there's no element in the codomain that is not matched to an element of the domain. So, for example, this is a onto function. And again, you can get the idea of many-to-one because there are many inputs hitting that one output. This function is a totally legit function, but it is not onto. And it's not one-to-one, right? Because there's certainly no unique answers. In fact, in this example, in this drawing, a one-to-one function is not possible. Because if you recall, the codomain has to be at least as big as the domain for a one-to-one function. Okay, well, there's a one-to-one function. So we say that f from x to y is onto if and only if for all y in the set y there exists an x in the big set X such that f of x equals y. So this for all y and y is what's forcing us to make sure that every y is covered. We can rewrite this as a universal conditional statement, which will make proving things easier. We say if y is an element in big Y, then there exists an x in big X such that f of x equals y. And what do we know about the relative sizes? Well, just from looking at this picture here, we can see that x can be bigger than y. And in fact, that is the requirement. We're going to say that the size of x has to be bigger than or equal to the size of y. Because if y were bigger, then there would be elements left over, right? These elements I'm drawing in that don't have arrows, in which case it's not onto. So that's not possible. So let's take a look at an onto function. Here's an example of an onto function. Again, notice that the domain is the integers and the codomain is the integers. What that means is we need every single integer to be the output of some input. So let's write that this is each element in the codomain is matched to an element in the domain. So again, we have this function here. Let's try f of 0. And we're going to get 0 plus 3. So when our input is 0, we're going to get a 3 out. How about if the input is 1? Well, f of 1 is going to be 1 plus 3 is going to give me a 4. And f of 2 is going to give me 2 plus 3, which is a 5. And we can also do negative values. Negative 1 plus 3 is going to be 2. So negative 1 matches to 2. And similarly, negative 2 is going to match to 1, and so on. So the question is, looking at this chart, will all values be reached eventually? Right? Is there some integer, right? Now, we're never going to reach 2.5, but that's okay because we're not expecting to. Our codomain is a set of integers. So we're not expecting to do that. But is there ever going to be an integer? Like, are we going to skip negative 5? No, we're there, an input of, what would that be? That would be negative 8 would give us negative 5. So we're going to have that. And there's not going to be any number that we skip. Now again, this really isn't a proof right here. This is an illustration. So let's prove it. Okay, so here we're looking at this function, f of x equals x plus 3. And I'm going to futz around a little bit on some scratch paper here. So I'm going to pull this aside. I'm going to say this is scratch paper. And I know that f of x is y. And it's also x plus 3. So I'm going to want to solve for x. And you'll see why when we get further in the proof. But I'm going to start my proof by solving for x. So if I subtract 3 from both sides, I get x equals y minus 3. Okay, let's move on to the proof itself. Again, we want to recall the definition of onto. We saw that right here, where for all y in big Y, or here we go, this conditional down here. I'm going to scribble it out so we can look at it up here. I'm going to say that this is true if y is a subset of big Y, then there exists an x in the set containing x such that f of x equals y. So we're going to suppose this part and show this part. So, suppose y is an element of our codomain. In other words, z, integers. right? That's our codomain. So suppose y is an element of the integers. Let's write this like this. We want to show that there exists an x in big X such that f of x equals y. Okay. Now, here's where our scratch paper work came in. Right? I want to show that there exists an x. That means if I can find any x, I'm not saying that all x have to do anything. I'm just saying if I can find an x that works, then we're good. Well, hey, I solved for x. Let's try this x. Let x equal y minus 3. Notice that since y is an integer, that x is an integer, due to integer closure properties. Well, so then what happens if we plug this x into our function? Now, again, I'm going to use the function definition where f of x is x plus 3, and our x is y minus 3, so I'm going to have y minus 3 plus 3, which is y. Well, that's what we were trying to show. We were trying to show that there exists an x such that f of x equals y. And you might say, well, you did that by magic. Or not magic, but you cheated, right? Because we took the problem and we figured out what the x would be. But that's fine. The place that these proofs are going to fall apart is in the domain, right? So this part right here, just as in earlier in this course, this is the part that will fail if the statement isn't true. So this is a really important part. And you have to include it. Okay, so this is which was to be shown. Well, it's looking very Christmassy, this slide, with all the red and green. Okay, so just like in the previous video, we're going to take a look at a problem where this is actually not true. And I'm going to try to prove that it is true in order to show you what it looks like when a proof fails. Okay, so we're going to say yes and then try to do a proof, even though we know that this really isn't going to work. Proof. So if you recall, the way we start is we use this universal conditional statement right here from the definition, and we're going to suppose the first part and then try to conclude the last part. So suppose, okay, let's write that up. I really like to have these definitions in front of me when I do this. So we say f of x to y is onto, if and only if y is in big Y, then there exists an x in big X such that f of x equals y. Okay, So back to our problem. I'm going to suppose this first part. Suppose y is any integer. We want to show that there exists an x in the integers such that f of x gives us y. That's the second part. Okay, well, similar to before, I'm going to get some scratch paper. So I'm going to make this little corner to be scratch paper. And I'm going to say, okay, on f of x is equal to y is equal to x squared. Let's solve for x. I'm going to get that x equals plus or minus the square root of y. So now let's look at our problem again. I'm going to say let x equal plus or minus the square root of y. So there's really two values here, right? So notice that f of x equals f of square root of y or f of negative square root of y. Well, let's take a look at f of the square root of y. And again, recall this function takes the input and squares it. So this is the square root of y squared, and that equals y. Okay. And if we do f of negative the square root of y, we're going to get negative square root of y squared. And what does that equal? Well, the real answer here, we could say, oh, well, that's going to be negative square root of y times negative square root of y. So this is going to be y. But we've got a problem. And the problem actually originated up here. We have to pick an input. We can't just do this thing like this. Actually, I misspoke. We can do that. What we can't do is, let's take a look at the domain. Is x an element of the integers? No. So this isn't going to work. So even though it looks like it works and we get y out, it's not going to work because of this not being an integer. So that's the problem. Now, again, this is not a proof. We just haven't been able to find one. We're not saying anything about all inputs. I'm saying, does one exist? Well, just because I wasn't smart enough to find it doesn't necessarily mean that one doesn't exist. So this is not a proof that it is not onto. It is a failed proof of my attempt to prove that it is onto. So to prove that it's not onto, we need to start over. So I'm going to say no. And again, I'm going to do a proof by counterexample. I guess that should be. Okay, let's try. I'm going to let y equal negative 5. Notice negative 5 is an integer, and so y is in our codomain. Does there exist an integer x such that f of x equals negative 5? Well, that means we have f of x equals x squared equals negative 5. Well, if we solve for x, we're going to get that x equals plus or minus the square root of 5. But the square root, negative 5. The square root of negative 5 is an imaginary number. So x is not an integer, for sure. And there's in fact no integer such that f of x is going to equal negative 5, which means that this is not on 2. Right. So this is a proof by counterexample. We found a number, negative 5, in the codomain, because the codomain includes all integers, but there is no integer that gets us to a negative 5 using this function. So this function is not on 2. And indeed, if you were to draw out the number lines, we can do this really fast. So this is like the pictures we had before. Zero squared is going to go to 0. 1 squared is going to go to 1. Negative 1 squared is going to go to positive 1. 2 is going to go to 4. Three is going to go to 9, and so on. So here are some more numbers that will never be reached. We're never going to reach those using our function. So this is most definitely not on 2.